This is a solar PV single-line diagram. The whole solar system drawn as one clean line from the panels on the roof all the way to the grid. If you have ever applied for a permit or booked an inspection for a solar install, this is the drawing they ask for. One page, every major part, every protection device, the way the power actually flows. So let us rewind it and build this solar PV single-line diagram up block by block, array, isolators, inverter, battery, distribution board, so that by the end you can read one at a glance and draw your own. First, why this drawing exists at all. You have probably seen a generic single-line diagram before. One line, standing in for all three phases of a building's power. A solar single-line diagram is that same idea, aimed at one job, the photovoltaic system. And it is not decoration. Three groups of people need it. The permit office needs it to approve the install. The inspector needs it to sign the system off. And you need it to size everything, the cables, the fuses, the breakers, before you buy a single part. That is the promise of the solar SLD. The entire system, honest and complete, on one readable page. So let us follow the power. Here is the whole chain, left to right, the way the energy travels. It starts at the PV array, the panels. From there it runs into a combiner and its DC protection. Then through a DC isolator, a switch you can pull to kill the panels. Into the inverter, which turns DC into usable AC. If there is a battery, it hangs off the inverter through its own fuse. Then out through an AC isolator, past the meter, and into the main distribution board in the grid. Every block on that line has one job and one or two protection devices guarding it. Learn the chain, and the whole diagram opens up. Let's take it one block at a time. Quick note before we do. Every symbol in this video lives in a free editor that runs right in your browser. CircuitDiagramMaker.app. No install, no sign up. Open it in a second tab, and you could drop these same blocks in as we go. The link is below. Block 1, the PV array. This is the source, the panels themselves. On the diagram, it is drawn as one solar module symbol, but next to it you write what it really is. How many modules? How they are grouped into strings. Panels wired in series to build voltage. And two numbers that matter more than any others here. VOC, the open circuit voltage, and ISC, the short circuit current. Why those two? Because every protection device and every cable downstream is sized against them. The maximum voltage the array can ever reach and the maximum current it can ever push. Get Voc and Isc on the page, and the rest of the drawing has something to size against. Block 2, the string combiner and the DC over current protection. When you have more than one string, their outputs meet at a combiner box. And right there, each string gets a string fuse, sized just above that string's ISC. So a fault in one string cannot be backfed by all the others. This is the first real protection device on the drawing, and it is the one inspectors look for first. On the single-line diagram, it is a small fuse symbol on each incoming string, feeding one combined line out. Fuses rated to the string current. Nothing exotic, but leave them off, and the drawing fails. Block 3, the DC isolator and a surge protection device. The DC isolator, sometimes called the DC disconnect, is a switch on the DC side that lets you completely cut the panels off from the inverter. It is there so anyone working on the system can make it safe. On the diagram, it is a switch symbol, rated for the array's DC voltage and current. Right next to it, we add a DC surge protection device, an SLD, tied to earth. Solar arrays sit out in the open, exposed to lightning and switching surges, and the SPD gives those spikes a safe path to ground before they reach the inverter. Isolator to disconnect, SPD to protect. Both belong on the DC side of the line. Now, a fork in the road, because not every solar system is the same. If your system is grid-tied or hybrid, the DC line runs into an inverter with a built-in MPPT maximum power point tracker, which squeezes the most out of the array and converts it straight to AC. That is the path most rooftop systems take, and it is the one we will follow. But if your system is off-grid, the array first meets a separate charge controller, which regulates the panels into a battery bank, and a separate inverter draws from that battery. Same symbols, different order. On your single line diagram, you draw whichever path is real, and you label it so the inspector knows exactly what they are looking at. Block 4, for hybrid and off-grid systems, the battery bank. The battery hangs off the DC bus, and between the battery and everything else sits its own protection, a battery fuse or a DC breaker, sized to the battery's maximum current, mounted as close to the battery terminals as you can get it. This is the most important fuse in the whole system, and here's why. A battery can dump enormous fault current, far more than the panels ever will. If a cable shorts, that fuse is the only thing standing between a fault and a fire. So on the single line diagram, it is drawn big and labeled clearly, battery bank, its voltage and capacity, and the fuse or breaker rating right beside it. Block 5, the inverter and the AC protection on its output. The inverter is the heart of the drawing, DC in on one side, AC out on the other, shown with that little sine wave symbol inside a box. Next to it, you note its rated power and its AC voltage. On the AC output, the same protection story repeats, mirrored. An AC isolator, a switch to disconnect the inverter from the grid side. An AC overcurrent device, a breaker sized to the inverter's output current. And a second surge protection device, this one on the AC side, again tied to earth. DC side, AC side, each gets its own disconnect, its own overcurrent protection, and its own SPD. Once you see that symmetry, the diagram stops being intimidating. Block 6, the main distribution board, the meter, and the grid connection. The inverter's AC output lands in your main distribution board, the consumer unit, usually through a dedicated breaker labeled as the solar supply. From there, the system ties to the utility, and in the middle sits the meter. On a grid-tied system, that meter runs both ways. It counts what you draw from the grid and what your panels export back to it. On the single line diagram, you show the point of connection clearly, where your solar system legally meets the utility, because that boundary is exactly what the interconnection approval is about. Board, meter, grid. That is where the line ends. And running underneath all of it, earthing and bonding, the part beginners skip and inspectors never do. Every metal part that should never be live gets connected to earth. The panel frames, the mounting rails, the inverter body, the isolator enclosures, all bonded together and tied down to the earthing system. On the single line diagram, this shows up as a green line or an earth symbol, reaching every block. Equipotential bonding just means all that metal is held at the same potential, so there is never a dangerous voltage between two things you might touch at once. It is the quiet safety net under the entire drawing, and on a solar SLD, it is not optional. Draw the earth every time. So step back and look at what you have. Standard symbols in a standard order. A module for the array. Fuses and a combiner. Switch symbols for the isolators. Little arrow to earth symbols for the SPDs. A box with a sine wave for the inverter. A battery symbol with its fuse. A circle M for the meter. And earth reaching all of it. That is the whole language of a solar PV single line diagram. And it is exactly why the drawing exists, because anyone who knows these symbols can pick up your page and read your entire system without ever seeing the roof. That is what the permit office wants. That is what the inspector checks. And that is what protects the people who work on it later. Let's recap the line. Array with its Voc and Isc. Combiner and string fuses. DC isolator and a DC surge device. The inverter, or a charge controller and battery for off-grid. The battery with its own fuse. Actini isolator, actini brache, actini surge davisa. Meter, distribution board grid. And earth, bonding all of it together. If you want the ground level basics of single line diagrams first, what one line and three phases really mean, watch our single line diagram tutorial, linked right here. And if you're wiring the panels themselves, the whole solar series is waiting for you. Then open the free editor, drop in the source, and build your own solar single line diagram. The link is below. Subscribe for a new diagram explained every week, and I will see you in the next one.